Hey guys, how you going? I just want to talk through this practical report. Basically, the way I'm going to work is just read through it and just highlight the points that I'm going to be talking about. So if there's a specific section of the report that you need some help with, just skip ahead through the video, get to the section that you need and listen, and hopefully it'll give you a bit of a hand. So the practical is about the reaction time between sodium thiosulfate and hydrochloric acid. What we're changing is the temperature, so that's our independent variable. So we're seeing how the temperature will affect the reaction time between the two chemicals. The way that we know that the reaction is completed is if it goes cloudy, because that's the production of sulfur. So those two chemicals are forming four products, and one of those four is sulfur, which is cloudy, so you won't be able to see that cross anymore. Okay, so this was the pre-lab stuff. So with your hypothesis, you just want to make sure that it's an if-then statement. So if the independent variable is increased, then the dependent variable will increase or decrease. Just remember, your independent variable is the temperature and the dependent variable is the reaction time. So I've got my independent variable thing there. Just make sure you put in the device used to measure the temperature, which is obviously what you're reading off of. I'll let you figure out what it is, and the units that you read temperature in. Guys, the dependent variable I've talked about already. It's what you measure, it's what you're recording in your results table. Guys, your controlled variables are the things that you're going to keep the same, consistent throughout your report. So those might be every time you did the experiment, what did you keep the same every time? You might talk about the fact that the method of timing is with a stopwatch, or to determine the endpoint is when the cross wasn't covered anymore. Materials are here. Safety, look up the SDS for these chemicals and you'll see the specific chemical risks. Usually the hazard symbols are what you're looking for. For example, the one with the arm with the little thing out of it and the little acid bottle on it, that's your corrosive. So one of these is corrosive. One of these is pretty dangerous in terms of being toxic, and one of them is actually quite harmless. So figure out what those are. Preventative measures to avoid chemical risks. It's what you're doing in the practical in order to avoid these hazards. So it might be to do with wearing your safety protection, wearing your gloves, that kind of thing. Other general precautions, just typical lab stuff that you need to be mindful of. So anything that you would be doing every single practical, that's what you want to write down here. Okay, so we did the practical, we've done the checklist. Good. So now we've got our results table. Guys, it's okay if you didn't fill in the whole table. My class, when they did the experiment, I didn't see anyone that actually filled all of the table, but you want to get as many data points as possible because it's going to make your graph a little bit better. So guys, you've got this. Just make sure when you're drawing your graph, you're only graphing your temperature and your average. Don't graph the trials, okay? The only point is to obtain an average here. Now guys, if you have 20 degrees and you have 5 and you have 6 and you have 7, your average, you add up the three results and then you divide them by 3, okay? So it's going to be in between, the number for your average is going to be in between all of these numbers. So the average of these three is going to be 6, okay? Just make sure you look at your answer for your average column and just make sure that it's in between these numbers. I mean, if I had an answer of 8, of 9, obviously that's higher than these three, so that's not going to make sense. Okay, you've got your average and you're graphing your temperature versus your average reaction time. You might just want to put the units up here. You don't put units in here. You don't write seconds or anything like that because it's in the actual it's in your heading here, so you don't need to do that. Okay. Now with your graph, you want to have temperature here and you want to have reaction time here. Usually it's dependent variable, independent variable, but for a temperature time graph, you always have temperature on the y-axis because I guess a thermometer, it usually looks like that, and then your reaction time on the bottom. That's just the way that it's done, so we'll stick to that. You draw a line of best fit through your data points. So if you've got multiple points, you use a ruler to draw a linear line of best fit, or you might draw a curve through your data points. You don't do a dot to dot like a zigzag. It needs to be a line of best fit through those points. Just make sure your scale is consistent when you're drawing. Okay, so this isn't the graph for the practical, but it just gives you some idea of, the kind of thing I'm looking for. You've got the axes labeled and you've got units on both sides. You can see that the scale is consistent. So this one's going up by tens, and every 2 squares is 10 units. And it starts at 0, 0, 10, 20, etc. Same thing for the temperature, okay? Remember, I would have swapped these two, have temperature on this side and reaction time on the x-axis here. If you look at your data points, they're pretty clearly plotted, and the line of best fit goes through the data. You can see that some data points are below and some data points are above. That's okay. The reason that they're not exactly on the line is likely to do with random error, so differences that occur throughout the experiment. So your results are never going to be perfect. You're never going to have all your data points exactly where the line should be, and that's good because that's saying, yep, there were some errors involved and this is what they were. So it's actually good for your prac write-up, okay? So make sure you have your graph. Remember guys, I want you to draw your graph and scan it in so you've got an electronic version. So everything is going to be submitted electronically. So the discussion, the first point here, using your graph, describe the general trend of the data. What that means is, I want you to tell me what your graph is saying. Now this graph here, as the temperature is increasing, so as it's going up, what's happening to the reaction time? So you start here, the temperature increases, what's happening to the reaction time? It's decreasing. So all you'd say here is, as the temperature of the solution increases, the reaction time decreases. And yours will probably look pretty similar to this, okay? Because the reaction time is how long it takes to happen. If it's hotter, it's going to happen more quickly, therefore lower reaction time. What is the shape of the line of best fit? Linear means straight, so just like this one was. Exponential means it's curved and it's kind of going upwards, so curving this way, so it's increasing more rapidly. Logarithmic is going the opposite direction, curve sloping downwards. Just Google those words so you can see the shape if you're not too sure what they mean, okay? Using your results table, look at the scatter, okay? So scatter is, like it says here, the difference between trial 1, trial 2, trial 3. And I want you to make a comment on your scatter. So here, if I had 5, 6, and 7, the fact that the numbers are so low, so 5 increasing by 1, that's like 20% increase, just going up by 1. So I would say that's high scatter, okay? If you had 55, 55, 56, and 57, the difference between 55 and 57 is not really that much. Yes, it's 2 just like before, but as a percentage, it's a little bit lower. So I'd say the scatter is low in that regard. If you had, say, 60, so 55 to 60, you might say that's moderate scatter, okay? So you just want to refer to it in that sense, and just refer to your data. So make it clear to me or your teacher that you're saying, okay, at 20 degrees Celsius, the difference between trial 1 and trial 3 was 5 units, therefore moderate scatter. Would you say the data contain, we just talked about that. Refer to your data when explaining this. Again, just clearly state. Don't state every number. If you've got all of these filled up with numbers, don't talk about all of them, but just pick a few ones to discuss and just talk about that for a little bit. Scatter is due to random errors. Identify 2 potential random errors. Random errors are ones that can occur throughout every single attempt of the experiment, and they can affect the result differently. It's usually due to human error. Random errors are unavoidable, okay? They're just going to happen. So because this reaction involved stopwatches, you can talk about reaction time, okay? Now, what were you looking for in the experiment? You were looking for when you can't see the cross anymore. So that's the end point of the reaction. When you see the end point, you stop the stopwatch. How long does it take? That's your reaction time. And that could be different every time, okay? Maybe one of the times you were looking really intently and you timed. Maybe one of the other attempts of the experiment, there was a bit of noise around you, or someone, I don't know, your partner hit you or something like that. Now, you don't need to say that, but it's that reaction time that can cause those random errors, okay? There are other random errors too, and I'll let you guys think about what they might be. This experiment involved measuring, so there's obviously some possible error involved in that. You're reading your measuring cylinder, you need to be flat at eye level. Sometimes you don't get that exact measurement, okay? You can talk about all kinds of things in terms of measuring and timing. Compare an average value with another group. So this is where you have to actually swap data. You might want to do this in class. Obviously, grab the numbers from someone else. You want to get someone that has similar temperatures. So if someone did 23 and you did 24, that's okay in terms of degrees. And then you just compare your average reaction time. Okay? Oh, sorry, yeah, the average reaction time. And just see how similar it is. Okay? The fact that it's different, it may have to do with, again, those random errors. Is there a way to know which group is more accurate? So what is accuracy? It's how close you are to the true value. Do we know the true value for this experiment? Okay, at 20 degrees, if you mix 5 ml of, what was the concentration of hydrochloric acid? I think it was 2 mole per litre hydrochloric acid, and your 0.25 mole per litre sodium thiosulfate, I think it was 15 ml. You've got this information here. So M means molar, that's what I'm talking about. It's just the unit for concentration. Basically how strong it is, okay? So if you mix the exact quantities of these two, how long should it take to react, okay? There is a true answer for it. How close are you? You probably don't know because, you know, you're not given the true value. You can't really Google it. There's just too many specifics that we've got here. So there might not be a way to figure it out, but you need to demonstrate in your report that you understand what accuracy means and the context to do with the experiment. A systematic error is one that affects the system, so it affects all of your results equally. So would there be a measuring device that if it's not correctly calibrated or incorrectly calibrated, it would have a bit of an effect? So possibly something like the thermometer, because you're always measuring the temperatures. So if the thermometer was off, say the thermometer read slightly lower than the real temperature every single time, that means all of your results would be a little bit lower than expected, okay? And if you compared to someone that had an accurate thermometer, all of your results would be different, okay? So you could talk about potential systematic error and how that affects the accuracy of the results. What an outlier is a data point that doesn't fit the rest of the data. Now, if you looked at this graph here, this is not an outlier. This is not an outlier. An outlier has to be way out, okay? So if you had these data points and then you had one here, that would be way out. And that might be to do with a complete kind of freak incident with the experiment. It's unlikely to have outliers because we're doing 3 trials, okay? If you did 1 trial, then it's more likely to get outliers, okay? You still want to explain what it is, so just clearly explain it. If there's none, just say no outliers are present in the experiment. One way to reduce the effect of random error, I felt like we tried to do this by doing the trials, so your sample size of 3, increasing the sample size and obtaining an average is going to be reducing the effect of random error. The presence of systematic error, how would you determine that you may have had systematic error? I talked about it previously in terms of obtaining data, comparing it with someone else. You could replicate the experiment, do it again on a new day with new equipment, compare and see if there is a difference. Suggest an alteration using more advanced technologies. Now this is something that we didn't really discuss or use in the practical. Is there any digital technology that would make this experiment more accurate, more valid, easier for you? Okay, so think of the devices that you used and manually read. Okay, so looked at something to determine a number, put it in your graph or your table. Is there an electronic version that we could use? Okay, there's one that we actually do have in the lab that we didn't use for this experiment. Okay, reflection, just be honest and just write how you think you performed in the practical and what you could do better and how you felt about it. Okay, just make sure you're looking at the rubric and see if you think you get an A for all of these points. If you would like me to explain what one of these means, just come up and ask, or ask your teacher. Thanks for watching, guys. Hopefully you got a little bit out of it. Good luck writing your report.